Welcome to our video presentation on ground segmentation using LiDAR sensor. We are Team SensorFusion, final year undergraduates from the Computer Science and Engineering Department of the University of Moratuwa, Sri Lanka. In this video, we will provide a general introduction to the ground segmentation domain, discuss the overall architecture of our project, explore various experimental approaches we followed, and our results. Ground segmentation is the process of distinguishing between the ground surface and all other elements, such as moving objects and man-made buildings. This process is essential for various applications, ranging from environmental monitoring to urban planning. By enabling us to understand, analyze, and make informed decisions based on the wealth of data collected by LiDAR sensors, ground segmentation plays a crucial role in leveraging LiDAR technology effectively. Let's look at two real-world examples where ground segmentation using LiDAR sensors is impactful. First, in agricultural drones, LiDAR technology can show detailed information about water stress, nutrient deficiencies, and issues like weeds or dry areas in crops. Second, in unmanned vehicles, LiDAR sensors allow these vehicles to navigate environments that might be challenging or risky for humans. Let's talk about the SensorFusion, the state-of-the-art deep learning model for semantic segmentation that uses the U-Net architecture. SensorFusion is designed for identifying ground and non-ground elements in 3D point cloud data. It uses a novel sparse self-attention mechanism that includes both local and spherical neighborhoods to capture the spatial relationships between points. This approach is particularly well-suited for non-ground segmentation tasks, as it enables the model to consider the global context while also focusing on the fine-grained details around each point.
This is a general U-Net architecture. U-Net is mainly used for semantic and image segmentation and many other applications. It has a contracting path and an expansive path. The contracting path has repeated 3x3 convolutions followed by a rectified linear unit and a 2x2 max pooling with stride 2 for downsampling. The expansive path has a 2x2 up convolution and also repeated 3x3 convolutions. At the final layer, a 1x1 convolution is used to map each feature vector to the desired number of classes. This is the general pipeline of the SensorFusion. First, SensorFusion has radial window partitioning. SensorFusion represents LiDAR point clouds using the spherical coordinate system and obtains a long pyramid-shaped radial window. Then, SensorFusion uses exponential splitting for the R dimension, which is the distance from the origin. This is for equally distributing the point cloud data because when the point cloud is far away from the origin, sparsity increases. After exponential splitting, SensorFusion uses dynamic feature selection. The model splits the point cloud into headers. The upper headers use the radial window partitioning, and the lower headers use the common cubic window partitioning. SensorFusion performs semantic segmentation on the input LiDAR point cloud data after the dynamic feature selection. It classifies each point into semantic categories such as sidewalks, roads, vegetation, buildings, and many other classes. Finally, the performance of SensorFusion is evaluated using metrics such as the mean intersection over union. Now let's dive deeper into our project workflow. Our journey begins with data acquisition and pre-processing. After thorough investigations of several LiDAR datasets, we selected Semantic Kitty as our benchmark dataset. Next, we move on to model selection. We've chosen SensorFusion as our ground segmentation model based on previous research due to its superior performance. The subsequent steps involved two parallel tasks parallelizing and optimizing the performance of the SensorFusion model and introducing an ellipsoidal windowing technique. This new technique replaces the traditional cubic windowing used in the state-of-the-art. To implement this, we first investigated the mathematical background of using an ellipsoidal window. Once we had a solid understanding, we proceeded with its integration. After completing these parallel steps, we focused on fine-tuning the model by parameter tuning and further optimizations. Finally, we conducted an overall evaluation of our model to assess its performance comprehensively. This pipeline outlines the systematic approach we followed throughout our project.
Next, we will present you the experiments we made in our project. In our first experiment, we focused on code optimization for reduced computational costs. We optimized the SensorFusion model to enhance overall performance by identifying and addressing several performance bottlenecks. The state-of-the-art model initially used 4 RTX 3090 GPU in parallel, but did not effectively utilize data parallelism. To address this, we applied various CUDA kernel optimizations, including memory coalescing and broadcast techniques. Most deep learning semantic segmentation models, including SphereFormer, use cubic windows to classify each point into semantic categories. However, when points are further from the origin, using cubic windows can be less accurate. SphereFormer addresses this issue by using spherical windows to represent LiDAR point clouds with the spherical coordinate system, creating long pyramid-shaped radial windows. In dynamic feature selection, SphereFormer uses both spherical and cubic windows on the point cloud. Our goal is to enhance the accuracy of sparse point cloud data by replacing the cubic window with an ellipsoidal window. To compare the existing cubic bounding box with the newly implemented ellipsoidal bounding box, the ellipsoidal bounding box can better fit the object than the cubic bounding box. This results in an increase in the intersection over union, or IOU value of the object. Continuing with our experiments, we now explore the concept of ellipsoidal windowing. In the existing SphereFormer architecture, the dataset is divided horizontally into several heads. A convolutional neural network is applied separately to each head. Radial windowing is used for the upper heads, capturing sparse data, while cubic windowing captures dense data in the lower heads. The combined features classify the data into 20 classes, and performance is evaluated using mean intersection over union values. Using ellipsoidal windowing enhances the accuracy of capturing complex and elongated objects. We've replaced cubic windowing with this advanced technique, allowing for a more precise capture of spatial data. The radial window accurately represents directional vectors, and the ellipsoidal box refines data encapsulation, especially for elongated objects. These components are then passed through a linear layer, producing an enhanced output and improving overall performance. Let's review the existing SphereFormer CNN architecture. It starts with a semantic model that uses uBlock to extract features, which are then passed through a linear layer for classification. The uBlock, functioning like a standard U-net, applies the sphere transformer using sparse multi-head self-attention sphere concat to extract features via cubic and radial indexing. The indexed point cloud is processed with self-attention functions, and the features are concatenated and returned. Our new implementation replaces the cubic method with ellipsoidal indexing, enhancing spatial data capture. The radial indexing ensures accurate directional representation, while the ellipsoidal box better encapsulates data, particularly elongated objects. These refined components are processed through a linear layer, producing an enhanced output, significantly improving the model's ability to capture and interpret complex and elongated objects, leading to better performance.
Next, we will present to you the results we got from our project. In our initial test of the SphereFormer model, we achieved a maximum intersection over union IU of 61.52%. As the first implementation, we applied ellipsoidal initial windowing, which increased the maximum IU value to 62.28%. Furthermore, by increasing the height ratio with respect to the width and depth, we achieved an improved maximum IU value of 62.84%. We analyzed the object class-wise MIOU values during the initial development and after each major development and integration phase. In here, we used 19 class objects using the Semantic Kitty dataset, which is derived from the Kitty Vision odometry benchmark. This dataset provides dense point-wise annotations for the complete 360-degree field of view of automotive LiDAR, enabling comprehensive analysis and accurate segmentation of various object classes. In this slide, we present the results of our CUDA optimization. First, we identified inference times and test MIOU values for each encoder-decoder stage by profiling the SphereFormer model. Through our optimizations, we were able to successfully reduce the inference times for stages 2 and 5. Additionally, we increased the test MIOU values for these two stages as well.
Now, let's take a look at the demonstration. This video demonstrates the raw input point cloud data collected via sensors on the left-hand side. On the right-hand side, you'll see the data after semantic segmentation has been applied. Each color on the segmented side represents a different semantic class, such as road, sidewalk, vehicle types, vegetation, and more.
This is our team. Thank you for watching.